Hello everyone. In this video I want to talk a little bit more about the concept of endo versus exothermic. Now, simply put, endothermic means that heat goes in and exothermic means heat comes out. And we could apply this to a lot of different situations. Probably the simplest is just a phase change or a change of state from solid to liquid and liquid to gas and that kind of thing here. So when we talk about something like melting, when solids turn into liquids, that's endothermic. You have to put heat into it and the ice melts. All right. The opposite would be freezing, and that would be to take the heat out of the liquid and make it turn into ice. All right. So any one of these processes could be considered endo or exothermic. On this chart, the blue arrows are endothermic and the green arrows are exothermic. All right, so there may be a question on the test related just to that right there. Is evaporation endo or exothermic? Is melting endo or exothermic? Something like that. And it's just a matter of, does the heat go in or does the heat come out? There's a number of different energy diagrams we could use to sort of illustrate this. One might be like a bar graph. In this bar graph here, we got a bar for solid and liquid and vapor. So this might be like ice, liquid water, and then vaporized water. And when you go from solid to a liquid, you have to put heat in, so that change in that, what we called enthalpy, was the difference between being a solid and being a liquid. Right? How much heat do you have to add to it? Now, that usually is given on a per mole basis, so the exact height of these graph here would depend on how much substance are you talking about, how many grams or how many moles of it. All right, but the difference in the heights on a per mole basis. Remember the one chart we had last time? It actually showed us the heats of fusion and heats of vaporization for water. So in the case of going from a solid to a liquid, this delta H right here, that's our heat of fusion, and that would be 601 kilojoules per mole, If you want to go from a liquid to a gas or a vapor, then you're talking about the heat of vaporization, 40.7 kilojoules per mole. Now we could have it kilojoules per gram too as well, and then it's just a different number. All right, this is like an energy diagram that we can illustrate differences in the amount of heat content or enthalpy between different phases or states of matter, in this case water. Now we could make what we call a thermal chemical equation, and here's an example. In the case here of water solid, if we add heat, and we wrote that right as 601 kilojoules, we can take the solid and turn it into a liquid. Right? This is known as a thermal chemical equation. And the change in enthalpy for that particular reaction is plus, because we had to put heat in, plus 6.01 kilojoules per mole. So we can speak of the change in enthalpy of a chemical reaction as well. If we have to put heat in, then we might put heat on the left side of the arrow and call it one of the reactants. And then the opposite, if we want to, say, take a liquid and turn it into a solid, that would be like freezing. In that case, the delta H, or the change in enthalpy for this reaction, is negative because heat has to come out. And if delta H is negative, we want to put the heat term over here on the right side. It's one of the products. All right, so you have to take heat out and to make a liquid turn into a solid, and you have to put heat in to make a solid turn into a liquid. All right, in either case, the delta H is the same, but for exothermic, when the heat comes out, the delta H is negative. And when heat is put in, then delta H is positive. Let's take a look at another reaction. Here's a reaction for the decomposition of water. We have liquid water decomposed into hydrogen gas and oxygen gas. And they tell us that the delta H, change in enthalpy, is a positive 285.9 kilojoules per mole of H2O. Now, we could, this reaction now has a positive delta H, which means that we have to put energy into it to make this reaction happen. Now, we could do this a couple of ways. I guess we could say H2O plus energy. I'm going to write it like that. All right, because it's if I just add heat to it, this doesn't happen. If you added heat to water, what would happen is it would just vaporize it, boil it, warm it up. All right, so in this case, I'm writing energy because it's a special circumstance. I'll show you here in a minute what that is. All right, so because delta H here is positive, then we have to put the energy on the right-hand side. Now, we could just as well write in the actual amount of energy, but if we put the amount of energy into the equation, we have to take into account that this delta H is per 1 mole of H2O. So what we would have to do is first balance this equation, and to do that I would add a 2 in front of H2O and a 2 in front of H2, and then it's balanced. So therefore, if this delta H for this is on a per 1 mole of H2O, then the amount of energy that I would need, if I'm going to write that in here, is going to have to be 2 times 285. Now I could actually do that math and write it down, or I can write it like this, having a 2 in front of it, kind of like the 2's are in front of H2O and H2 as well. All right, so sometimes we'll just write the word energy or heat, and sometimes we could actually write the actual number in there. Technically, I suppose I should put the units with it too as well, kilojoules. All right, now if I'm doing that, I don't need to write kilojoules per mole, because that's sort of taking into account the fact that I have 2 moles of H2, and that's how much energy I would have to add then, if that were the case. Now, this reaction can actually go the other way too as well. We could take the H2 plus O2 to yield H2O. It's exactly the same reaction, but backwards. Now, in this case, the delta H for this one is this reaction is going to be exactly the same amount, but going to be negative. Now it's exothermic. Heat comes out. So if I want to put the heat term into the equation, I have to put it over here on the right-hand side. Heat is produced, or energy is produced in this reaction. If I want to write in actual numbers, then I would do it just like I did before. 285 times 2 kilojoules. All right, so this reaction could go both ways on there too as well. This right here is a device that actually does that very reaction both ways. It's called a fuel cell. All right, what is it? It basically has 2 little chambers of water on the bottom there, and when we run some electricity through the water, we can make it produce hydrogen and oxygen. All right, now to make that happen, that's the reaction up here on the top. So we have to put energy in. The energy could come from, say, a battery. So if I hook up this battery to this, we can actually make some hydrogen. Let me hook that up here. Put the plus on there, negative on this, and it's set to go. All right, so now current is flowing through the fuel cell, and it's making hydrogen. Now it's a little hard to see here, but underneath on the bottom, that little chamber is pushing water from the bottom to the top, and the bottom is filling up on this side with oxygen, on the other side with hydrogen. So the water gets pushed from the bottom chamber to the top chamber, and then the little airspace up there is actually oxygen. So it's actually it's doing this reaction right here. It's taking H2O and decomposing it into hydrogen and oxygen. To make the reaction happen, you have to put energy in, and the energy comes from the batteries right there. All right, we're going to give it a second here and wait until it finishes charging all the way up. Okay, we're almost there. The hydrogen side is now just putting bubbles up through the top, and the oxygen side is almost done. It always makes twice as much hydrogen as oxygen, as you can see from the balanced equation on there. So now what we can do is we can stop the input of energy on this and reverse the process. Now, instead of putting energy in, I'm going to get energy out, and I'm going to hook it to this little fan blade over here, and the energy out is going to now turn the little fan blade. So now we are doing the bottom reaction, and the hydrogen and oxygen are being recombined, synthesized into water once again. So the little water chambers on the top, the water will flow back down into the bottom as we use up the oxygen that's down here in the bottom of the chamber. So we got endo and exothermic. Now it's not necessarily heat that's going in and out, but it is energy, and we still could call it endo and exothermic. So for the endothermic reactions, delta H is plus, and if we put it into the chemical reaction or the equation, we want to put it on the left side. For the exothermic reactions, heat comes out and delta H is negative, and we put the heat term or the energy term on the right-hand side of the equation. Here's another reaction that we've talked about before. That is the combustion of propane, C3H8. And the heat of combustion, which we had talked about before, is, let's see, propane here, 219 kilojoules per mole of propane. Now, in this case, the delta H is negative. All right, notice that all heats of combustion are negative. That means that all combustion reactions are exothermic. They give off heat. All right, which is, why we burn stuff, to get the heat out of it. So if we were to try to put the heat term into our equation, should we put it on the left or should we put it on the right? Because delta H is negative and heat is produced, we're going to put the heat term on the right-hand side. Now, I could write it as kilojoules, or I could just write out the word heat too, and it would make sense on there. So sometimes we write just heat, sometimes we write the actual number. Kind of depends on what we're trying to illustrate there as well. So combustion reactions are exothermic, and they have a delta H, or a change in enthalpy, and in that case they're always negative. They're always negative. Now, question, are there some reactions that are in fact positive? Delta H is positive, endothermic. Okay, let's take a look at some cases where the reaction may actually be endothermic. In some cases, when you dissolve compounds, for example, in this reaction here, NaCl, sodium chloride, or regular salt, the delta H for this reaction is positive. We call it a heat of solution. Sometimes when you dissolve stuff, it makes the water get hotter. Sometimes it makes the water get colder. It kind of depends on the substance. All right, here's a chart that shows some heats of solution for some various compounds. Now, sodium chloride doesn't give off or take in a lot of heat when you dissolve it, but what would it do to the water? Would it make the water hotter or colder? So if I take the sodium chloride and I put it into water, it should make the water colder. So let's give it a try and see. Now, the delta H is not large for this reaction, so we might not get a lot of change. But right now I have a thermometer in some water, 19 degrees, pretty much room temperature. Let's see if dissolving this actually makes the temperature get colder. Oh, look at that. It's already going down. 18.6, 0.4, 0.3, 0.2. So it is actually cooling down the water when it dissolves. So this is an example of an endothermic. Why is that endothermic? All right, to make the water dissolve, you have to put heat into it, and therefore the heat term, if we put it into the equation, is on the left-hand side, and the heat is going to have to come out of the water into the dissolved ions, So if heat comes out of the water is going to get colder. All right, so as far as the water is concerned, it's losing heat. All right, that's kind of exothermic. But as far as the sodium and chloride ions, they are gaining heat, so that's endothermic. So the dissolving process is actually endothermic, and it makes the water get colder. Now, if you look at the chart, any of these other substances on here, if their delta H's are negative, then when you dissolve them, they would make the water get hotter. All right, and it can go both ways. Later, when we study acids and bases, we may come back to this and talk about this a little bit more as well. Some of you may have seen or used these kind of cold packs before. They work on this very same principle. All right, the reaction is the dissolving of ammonium nitrate. If we look at the chart, ammonium nitrate, NH4NO3, is on this chart, and the value for delta H is 25.5. So delta H for this reaction, and notice in this case plus 25.5, and that's kilojoules per mole of the stuff dissolved. And because it's plus, heat should actually be inserted on the left side of this. So it's going to take in heat, and it's going to take the heat out of the water that's trying to do the dissolving. Now, here's the question. How does this cold pack work right here? Here's one of them. I got this one at Walgreens. Now, if you've ever used these, to make them work, what you do is you got to squeeze it. And there's a little pouch of water inside there and some chemical inside there too as well. All right, rather than squeeze it, I'm going to cut it open and let's take a look. All right, I'm going to just snip this thing open so you can see what's inside it. All right, first off, a little pouch of water. And then inside there are crystals of the ammonium nitrate. All right, here's what I'm going to do. I'm going to take that ammonium nitrate and put it into my flask. All right, I'm going to put it into my beaker right there. And then normally what you do is just squeeze this. I'm not going to squeeze it though because the water will go everywhere, but I will cut a hole open in it. And then I'm going to, wait, I got to do my thermometer. Let me get my thermometer in there. All right, let's see what the temperature of this stuff is right now. Probably close to room temperature, 19.8 degrees. All right, a little hard to see there. Let me see, adjust that. All right, 19.9 degrees. I'm going to pour in the water. So once you broke the bag inside of the big pouch there, these two things would mix. And then what you're supposed to do is shake it up. All right, then you shake it up, and then the ammonium nitrate starts to dissolve. And because it's an endothermic process, the heat has to go into the dissolving of the ammonium nitrate, and that heat's going to have to come out of the water. So what will happen is that the water will get colder as it gives off its heat to the dissolving process. So dissolving ammonium nitrate is quite endothermic. In this case, it gets quite cold. If you've ever used one of these cold packs, you realize that That's how they work. All right, that's how they work. Now, once all the stuff is dissolved and the heat has been transferred that's going to transfer, then dissolving will probably stop, and then eventually it will wear off and then stop getting any colder. But the heat, the coldness of it will last for a little while, and you can put it on your, sprained knees and ankles and stuff like that too as well. All right, so the dissolving process is endothermic. All right, endothermic. All right, if you were to put this on your knee, say for example, it would it would feel cold. All right, why does it feel cold? It feels cold because heat is going into it. Heat is going into it, and if you touch it, the heat comes out of your hand or your knee or your ankle, and it feels cold to you because heat is going into the pouch and coming out of your knee, and as far as your knee is concerned, then it's undergoing an exothermic reaction, giving away heat, and the pouch is undergoing an endothermic reaction. It's taking in heat. There you go, the instant cold pack. Have you ever seen one of these? This is the opposite. This is a hand warmer. It's designed to make you feel warm. All right, how do these things work? All right. There's lots of different brands of them, but here's the reaction that's actually happening in this thing. All right, when you expose it to air, oxygen, this reaction happens, and it happens to be exothermic. Now, I already pre-recorded a little demonstration with this, so let me show you that right here. Today we're investigating the Hot Hands brand of hand warmers. If you've ever used one of these things, the way they work is there's a little pouch, and you take it out and you kind of shake it up like that, and the air reacts with the stuff that's inside of the thing. All right, let's look at the package here and see what it says. Heats up to 10 hours of heat, air activated, safe, natural heat. All right, let's look at the ingredients. Iron powder, water, salt, activated charcoal, and vermiculite. And they say that the average temperature is going to be 135 degrees Fahrenheit or 57 degrees Celsius. That's pretty close to the average temperature of the water coming out of your faucet. All right, let's do a little bit of investigation on this then. This one's been activated for a while, so we're going to use a different one. Let me pop out the other one. Each pouch comes with 2 of them. And as soon as it's exposed to the air, it should start to activate. It does take a little while to get warm. We're going to record the temperature of it using a lab quest right here. All right, what we'll do is this. I set this up so that I could record for, let's say, 3 hours. And it's going to record 30 samples every hour, so I'll say every 30 seconds. All right, I'm going to start it up right now. It's measuring 20.1 degrees. That's pretty much just room temperature now. The thermometer is right here. And what I'm going to do is get this thing a little bit activated here. And it's just starting to warm up. And I'm going to wrap it around in thermometer, and then it's going to record the temperature every 30 seconds for a few hours, and we'll see what kind of data that we get. I'm going to wrap a rubber band around this so it can hold on there nice and tightly. All right, there we go, and we're just going to let that sit then for about 5 hours, and we'll record the temperature, and then we'll come back and take a look. Now, it is a hand warmer, so I think we should include a hand with the experiment. Oh, here's one. All right, so we're just going to include that with it as well. All right, let's look at a little bit of the package while we're waiting for it to warm up. It says that you can use this for snowboarding, skiing, fishing, camping, looks like golf, raking, and backpacking or hiking. I was kind of hoping to use it while I was out in my kayak, but they don't have an icon for that, so dang it. Oh well, maybe we'll try to find a different brand. All right, we're just going to let this go and record the temperature over a period of 5 hours. See you in a bit. Okay, I did let it go, but not for 5 hours. And here's the resulting graph. All right, notice what happened, that it took a while for it to warm up to its temperature, about a half an hour, and it was up to its max, which looks to be about 54 degrees, and then it stayed at that for almost 3 hours. There it says that it's supposed to last for 10, but my timer ran out, so assuming that it would just stay that warm for that period of time. There you go, hand warmer. All right, now let's look at that reaction. Now, what's inside of the thing? Inside is some iron powder, and when you open it up, air gets to it, and the air has oxygen, and that's what's actually reacting there. And it's an exothermic reaction. Now, I looked up the delta H for this reaction, and it turns out to be 824 kilojoules per mole of Fe2O3. Now, because it's negative, if I want to write the heat term into this equation, I'm going to put it on the right-hand side. It's negative. It's exothermic. It gives off heat. All right, it gives off heat. Now, that's per 1 mole. If I have a balanced equation, I may have to adjust that a little bit, though. What I mean is this. To balance this, what will I have to do? I'm going to have to put a 2 in front of that. And nope, I'm going to have to put a 3 in front of that, a 2 in front of that, and then a 4 in front of that. All right, that's a balance there like that. In which case, the amount of heat that I'm going to make, because it's per 1 mole of this, I'm going to have to double that amount. So instead of writing heat, if I want to write the actual number, I'm going to have to take 2 times 824. And then I would put that in the equation if I want to put the amount of joules or kilojoules in there instead of writing the word heat. All right, there you go. That's an exothermic reaction. Here's another kind of hand warmer that is actually reusable. This one is a pouch of liquid. Now, what's the liquid? The liquid is a supersaturated solution of sodium acetate. And to make the hand warmer work, there's this little piece of metal right here, and if we kind of bend it or give it a little click, you can see all of a sudden that the supersaturated solution now is turning into a solid, and crystals of sodium acetate are growing as it becomes solid from soluble to non-dissolved, and it's exothermic. It gives off a lot of heat, right? And it's a hand warmer, and you can feel that heat. To reuse it, you simply put it in a water bath and use it over again. Okay, before we leave this, I want to show you one more type of graph you might see on the test. It's kind of like the bar graph, except it shows a couple other things. All right, if I make a bar for the reactants, consider the endothermic reaction of the cold pack. I have the reactants at a certain amount of energy. All right, so there's a certain amount of energy stored in the molecules of the reactants. And then after the reaction, there's more energy in the products. So the energy actually goes up. The energy actually goes up on this kind of a graph. So as this reaction proceeds, I start out with something lower, and then heat has to go into the reaction, and I end up with products that are at a higher energy. So the products represent by the height of this side of the graph, and the reactants on this side. So the fact that this is lower and it ends high means that that's an endothermic reaction. All right, now if I consider the other reaction, it's an exothermic reaction, and delta H for it is negative. Delta H for it is negative, and the products have less energy than the reactants. So if I make a similar type of graph, I'm going to start high with the reactants and end low with the products. All right, so the reactants have more energy. In this case, that's the butane and the oxygen, and the reactants have more energy than the products. Now, I'm going to connect these in a little bit different way though. So after the reactants, I'm going to put a little hump up here and it's going to go down like this. All right, now what does this mean? What does this mean? All right, what this means is that the reactants have to first increase in energy a little bit somehow before the reaction can actually go and make products. All right, now how much energy? That's the difference between this right here. How much energy is that? All right, we're going to call that activation energy. The difference between the energy of the reactants and the highest point here is the activation energy. That's the energy needed to make this reaction happen. Here's one of those little lighters that contain butane. All right, to make them work, you have to roll your thumb on this little roller here. And what the little roller does is creates a spark. The spark provides the activation energy to get the thing going. This little lever right here, that little lever makes the gas turn on. So when you push it down, gas is leaking out. If you roll and push it at the same time, you can get the thing to light. Like that. If you just roll it without pushing down on the little lever, you can make little sparks. They're hard to do with one hand, but so the little flint thing provides the activation energy to get the reaction going. All right, once the reaction goes, then the heat from the one molecule burning can provide energy for the next molecule, and then the thing just keeps on going all by itself like that. So activation energy. Sometimes to make reactions go faster, we can do a few things. If I heat up the reactants, then it will shift it can shift the reactants a little bit higher as you give them a little more energy. Now they got energy in their stored bonds, but there's also energy in their molecules. And if you, to get that bar get a little bit higher, you might get it closer to the activation energy as well. All right. So remember this, that if you start high and you end low, that's an exothermic reaction. If you start low and end high, that's an endothermic reaction. Now this endothermic reaction didn't really have much of a activation energy. All right, it might be kind of small, so very quickly and easily, as soon as those things are mixed, they pretty much start to go all by itself, and very little activation energy in it. All right, so you might see that kind of diagram on the test. We'll do a little bit more review on that before the test as well. All right, that's all I got for you today, so thank you for watching.